Torsional strength. Torsional strength is the ability of a material to resist torsional shear. Torsional shear occurs in rotating parts. Think of the drive shaft in your vehicles. It is a rotational twisting force. If you look on page 51, figure 4.7, you'll see it gives a good explanation, a good demonstration of a graphic of that torsional force. It's got the force going one way on the shaft and the force going the other way on the other side of the shaft, causing the stress to occur right in the middle of the shaft, and that's where the failure would happen. So there's a formula for figuring out torsional strength. The formula, you have to find J, and J is the polar moment of inertia. And that formula is J equals pi times the diameter to the fourth power, and you take that and divide that by 32, that gives you J. Then you go back up to that top formula that I got there right up there on the slide, and to find the max torsional stress, that equals T, which is the torque, foot-pounds, inch-pounds, whatever the measurement may be, and you multiply that times the radius of the part, and then you divide it by J. So, what is the torsional stress on a 0.250 diameter with 200 inch-pounds of torque applied? Well, we'll open up the calculator. And I had to switch to an online scientific calculator to do the diameter to the fourth power. So here's an online calculator. So the formula again was pi times the diameter to the fourth, right? So we'll go down here and we'll go pi times, the diameter was 0.25, quarter-inch rod, 0.25, and on your calculator it might be an x with a y up here as the exponent. This one has a y with the x, so 0.25, and that is to the fourth power, and that equals the top part. That doesn't look right, but we'll keep going. Divide that all by 32, and it is right. Okay, so it is 0.00038. So we're going to round this to 4/10. 0.0004. 4/10 thousandths, tenth of a thousand. All right, so then we go back. So now we'll use the T times R divided by J to find the max torsional stress on this part. So T is 200 pounds. And we multiply that times the radius of the diameter, so that'd be 0.125 is the radius, so 200 times 0.125, and I'm just going to do this on my calculator off screen. And 0.125 times 200 equals 0.25, and then we take the 25 and we divide it by J, and J was 0.0004. So divide that by 0.0004, 4/10 equals, and I got 62,500. 62,500. Now, it depends where you round, and but as long as you come up with a number that's close to that, I know you did the calculations correct. Okay, flexural strength. It's defined as a bending strength. It involves tensile stress on one side and then compressive strength on the opposite side. Look at the example on page 51 for 8. And you can see the load is compressing down on the part, but the tensive strength is underneath as it pulls apart on the axis underneath. Regularly seen in structural beams and long parts in machines. Now there's a formula for that too. So flexural stress formulas is capital M times lowercase c divided by I. Okay? So M is the bending motion in inch-pounds. C is the distance from the neutral axis of the member in inches. Again, basically, it's just the radius. I is the moment of inertia. And again, I equals pi times the diameter to the fourth power divided by 64 this time, not 32. Okay, pi times the diameter to the fourth power divided by 64. You can look at the example on page 51. Okay, right in the middle of the page on the right side. So the combination of the tensile stress on the bottom and the compressive stress on the top of the part is called flexure. Flexural stress, M times C divided by I. Here's the formula again. Find I first, the moment of inertia for a circular cross section. Okay, with all that being said, what is the flexural stress of a 2-inch shaft, and the applied moment at the break point is 96,000 inch-pounds. And I'm going to give you a couple seconds and let you figure that out on your own. Now, depending where you rounded, you should get a number between 122,231 to 122,293. Okay, as long as you're close to one of those two numbers or in between, you did your formulations correct. If not, go back and redo it again. Stress comparisons. So fatigue or endurance strength refers to the ability of a material to withstand repeated loading and unloading. Vibration causes fatigue stress. Toughness and impact strength measure the ability of a material to absorb or resist that shock. Go ahead and look at your figures 4.9 and 4.10